Hey guys, how you doing? It's Mr. Lee. Here's our video on section 5.1, producing data. And I like to call this chapter designing studies. So in section 1, we're going to talk about samples and surveys, so basically observational studies. And then in section 2, when I lecture at you guys live, we're going to talk about experimental design. So in section 1, we're talking about samples, and in section 2, we're talking about experiments. So here's our objectives. We want to make sure that we're able to identify the difference between the population and the sample. Then we also want to look at identifying voluntary response samples and convenience samples, that is bad samples. And then we want to look at good sampling techniques. So we want to describe how to use a table of random digits to select an SRS. And we want to also learn about other good sampling methodologies, which include stratified random samples and cluster samples. And finally, we're going to explain how undercoverage, non-response, and the wording of the question can lead to bias. And we're going to define what bias is in a survey. Okay, we're not going to do this. So the big idea about sampling is that it's not efficient, and sometimes it's not even possible to ask every single person in the population a particular question. So when you're trying to study, you're doing a statistical study, obviously the first thing you have to identify is, well, what is our question of interest? What do we want to know? Right? So we have to define our question of interest. And then we also have to define our population of interest, like who is it that we want to know something about? And the population is everybody that is in that group of who we want to know something about. But again, it's not practical to ask every single person. If we did that, that would be called a census, just like the census that we do in America, where every 10 years the government tries to take a census and tries to figure out, some important information about, the population, not just the population, but also the demographics. And there's also some other information that they try to glean from the census. Well, obviously, one of the big problems with the census is they only do it every 10 years because it's extremely expensive to try to basically survey 330 million people in the United States. And it's not very efficient either. It takes a really long time to gather all that data. So what we do instead is statisticians use what's called sampling. And so a sample is part of the population that we actually gather real data from. So actual observations come from the sample. And it's really important, like how we select the sample. It has to be done in a very particular way. And it turns out that there's three, kind of valid ways that we're going to discuss. There's the simple random sample, the stratified random sample, and the cluster sample. Okay, but how you select the sample is very important because we want the sample to be representative of the entire population. Okay, and then from the sample, we gather data. So we get our actual observations, we get our raw numbers, and then we summarize that data and we use statistical modeling to make conclusions about the sample data that we get, and then we make inferences for the entire population. And what does making inferences mean? That means we make statistical conclusions, statistically valid conclusions that are backed by the math, that are backed by the laws of probability and the laws of calculus, the properties of calculus, that back up all of statistics. Okay, so this cycle is very important, and this visual is very good, very strong graphic, especially for visual learners. So we have the entire population, we take out a representative sample, and then we gather data from the sample. We summarize that data and analyze that data using statistical modeling. And then we make an inference about the entire population. You never make an inference about the sample. You don't have to infer something about the sample because you already have the actual data from the sample. So that's why the inference is always about the entire population. And that sounds like a trivial point right now, but when we get into inference, that's a hugely important point to remember. So the idea of a sample survey is that obviously we want to draw conclusions about the entire population. We want to choose a sample from a large, varied population, but it's not easy to do properly. Okay, so step one is we want to go ahead and define the population of interest. Step two, we want to say exactly what we want to measure. Okay, so exactly what is the data that we're going to have to be gathering. Okay. Then step three, decide how to choose a sample from the population. And there's three valid ways. But before we talk about the valid ways, we're going to talk about invalid ways, like bad ways to sample. What are ways to sample badly? Okay. So the first bad way would be called a convenient sample. And a convenient sample is exactly what it sounds like. You would just sample like the most convenient, people that are nearby you. Okay, so if you wanted to know, for example, if your population of interest was, hey, I want to know something about all high school seniors in the Tri-Valley area. So I'm going to define that population a little bit further to include all currently enrolled high school seniors at the following high schools. Amador Valley in Pleasanton, Foothill in Pleasanton, Dublin High School, and then we could say Cal High, San Ramon Valley High School, Monte Vista High School, and what else? I think there's a couple other high schools in the Tri-Valley area. Oh yeah, Livermore High School, Granada High School. But we could, very clearly define the population of interest. And is it really practical for us to go around to every single senior's house and, ask them to fill out a survey? No, it's not. It's not. So we're going to choose a representative sample. But a convenient sample would be like, hey, I live in Dublin and I live really close to the high school. So why don't I just, go to some houses that are right around Dublin High School? That's convenient, but that's not representative of the entire population. So that's the problem with convenient samples. So we also have to define bias, and this is critically important. This is definitely worth writing down and memorizing basically what our definition of bias is. So bias means that there's something in the design of the study that systematically favors certain outcomes. Okay, there's something in the design of the study, the way the study itself was designed, that systematically leads to a particular conclusion or a particular outcome. Okay, and that is what bias is. So voluntary response samples are not good. We do not want to have what's called voluntary response because that's going to lead to bias as well. Okay. So a voluntary response sample, it's when people are self-selecting, where the respondents are self-selecting. Okay, they respond, they volunteer to respond. And the problem with allowing people to volunteer to respond is that most people won't respond, but the people who do choose to respond typically have very strong opinions. And usually they have typically very strong negative opinions. Okay, sometimes it's people who have a very strong positive opinion towards a particular subject or topic, but it's usually the people who have very strongly negative opinions towards whatever the topic is or whatever the question of interest is. Those are the ones who will typically self-select, and then obviously there's going to be a huge amount of bias in there because the data that you gather is all going to point you towards the wrong conclusion. So, for example, if our population of interest was all high school seniors, in the Tri-Valley area, and you did a voluntary response sample asking, um, hey, do you prefer, how do you like this sports drink made of coconut water called Body Armor, right? And a lot of people are not going to volunteer to respond to that. And then probably the people who do volunteer to respond are the ones who have tried it, who hated it. And so you're going to systematically get a particular outcome. Okay, so those are things we want to avoid. So the first thing that we want to have in our sampling technique, and this is super important, is our definition of randomness. Okay, our definition of randomness. So the definition of randomness is something you definitely want to write in your notes and you want to memorize. So the definition of randomness is basically that for something to be truly random, for an outcome to be truly random, every individual has to have the exact same probability of being selected, and every subset of size n individuals also has to have the exact same probability of being selected as every other subset of that same size n. Okay, and that's a little bit redundant because every individual, that just means n equals 1. Okay, but for it to be a truly SRS, a truly simple random sample, for it to be random, then everyone in the entire population has to have the same probability of being selected, and every subset of size n. So for example, if we want to know something about all high school seniors in the Tri-Valley area, then are we going to sample just one person? Is our sample going to be of size n equals 1? No, we want to have a representative sample. So that's another thing, is like if you have a sample size n, little n, that's too small, well, that's not going to represent the entire population either, right? There's some minimum size that we need to have for us to feel as statisticians that yes, this sample size is large enough that we could say it represents, the entire population. And why don't you think about like how big would you be comfortable? Like what's the minimum n that you would be comfortable with? And let's think about n not in terms of a count, but in terms of a proportion or a relative frequent. Like how much, how many, like what percent of students do you think we would have to have? Do you think it'd be 50%? Do you think it'd be 75%, 90%, 30%? What do you think? Well, it turns out there's not just one number, okay, that all statisticians agree on, okay, because it kind of depends on what the study is. Is it an observational study? Is it an experiment? Like, what is it? But generally, like one number that you can kind of have in your brain, generally we're looking at least 10%. Okay, 10%. Okay, but again, don't worry about memorizing that number. We'll talk about what the minimum n is, what the minimum sample size is when we're talking about different situations and different scenarios. Okay, but let's say that let's say that we discovered that there's, I don't know, 5,000 seniors in the Tri-Valley area. Well, let's say that we want to have a sample size of size n equals 500, so 10%, right? 500. So we want to have a sample size of n equals 500, and so for it to be a truly random sample, we have to have every single combination of 500 seniors out of that 5,000. They all have to have the exact same probability of being selected. All of those subsets of 500 seniors in the Tri-Valley area. Well, how many, those of you that have taken, more advanced math classes, you're already thinking about, well, how many combinations of 500 can I draw from a population of 5,000? And it's a big number. It's a really big number. You've probably studied or at least been introduced to some basic combinatorics, which is actually a really interesting field of mathematics. But you probably remember way back in pre-algebra or in Algebra 1, your teachers, teaching you the terminology of combinations versus permutations and how to calculate those. Maybe it was Algebra 1, maybe it was Algebra 2, but somewhere in there, when you're learning sequences and series, you probably were taught a little bit of combinatorics. But on your calculator, it turns out we can calculate that, the number of combinations. So it's just in math. I think it's in math PRB probability, but it's 500. Like I have my calculator right now, so I'll just put in 500 math PRB NCR, okay, which is the combinations, and PR is permutations. So 5,000. So 500 NCR, 5,000, and there's too many. You get an overflow error. Actually, it's 5,000 NCR, 500, excuse me. But you get too many. It blows up your calculator. You get an overflow error. But anyways, how do we actually ensure that our sample is random? Well, can't we just use like a random number generator? And I know some of you already know how to, like one of your colleagues actually shared a program that he wrote in Python where he imported a math library into Python and used the random number generator in Python. And your calculator actually has a random number generator, right? It has a random number generator. If you go to math, PRB, and scroll down to randint, which is number 5, randint, and I'll go 1, 9. So that's just selecting a random integer between 1 and 9. So can't we just use our calculator to generate random numbers? Well, it turns out that your calculator and computers actually are not random. Okay, even the random number generators in Python and in on your TI-83 or 84, they're not actually random. Okay, they're close to random. They're very close to being random, but they're not actually random. The reason why they're not random is because they follow an algorithm to choose a random digit. Okay, and what I like to do in class is I like to have all 30 of us sit in class, and I'll say, okay, everyone push on your calculator, math PRB randint 1, 9, and we'll do this several times, and you'll see that when 30 students do it, you'll see lots of repeats and lots of people getting the exact same quote unquote random integers coming up and in the same order. Okay, and so you can see that the random number generator function on your calculator is not truly random. So there is actually a way to get around this so that there's not a definable pattern where everyone's getting the same random digits, and that is what is called seeding your computer. And I'll go over that next time when we're in class. But seeding your computer basically means your calculators are all going to follow the same algorithm to choose a random digit, but the starting point from where your calculator starts is called the seed. And so we can all start from a different place. So we can seed our calculator. Okay. And usually what I do is have people put in like their 10-digit phone number or their zip code or something like that. So as a seed, just so it starts from a different place than everyone else's calculator. Okay, so an SRS is the first most basic. It is, but it's very important. It's the first valid way to draw a random sample. Okay. And now for us, the only truly random thing that actually meets the definition of randomness is what's called the table of random digits. And the table of random digits is actually just an excerpt from the book of random digits. And the book of random digits is basically an entire book. It's a tome. It's like a huge book. And it's basically just randomly selected digits from 0 to 9. And it's basically like one digit was selected, then the next digit, then the next. All these digits were randomly selected, and it's just one long, super long string of randomly selected digits. And it goes on and on and on. And so what we have is table B, which is the table of random digits, and that's an excerpt from the book of random digits. And so if you just turn to table B now, I think it's in the end of our book, but what you'll see is that it doesn't look like one long string of digits, but it really is one long string of digits. But to make it easier to read, okay, we've like chunked out the numbers into 5 digits at a time, and we've put line numbers. Okay, and so that's important because on the AP exam, they're going to give you an excerpt of the table of random digits. And like, if you think about it, like if the AP exam question said, okay, student, use the table, use table B to, randomly select a digit from 0 to 9. Well, obviously that wouldn't work on an AP exam question because everyone would put different answers, right? If it was truly random. So what they're going to do, the type of question you'll get on the AP exam is they'll show you an excerpt of the table of random digits, and they'll say something like, starting on line 174, reading from left to right, okay? And then they'll give you exact instructions so that everybody lands on the same digits. Okay, and then obviously it's a question that can be graded. Okay, so we're going to use the table. We're going to use table B. Okay. So table B, like I said, it's a long string of random digits, 0 to 9. Each entry in the table is equally likely to be any of the 10 digits 0 through 9. So each individual number has the same probability as each other individual number. Okay. The entries are also independent of one another. That means that, and this idea of independence is critically important. Independence simply means that one outcome has no bearing on another outcome. Okay, so if you look at the table of random digits, let's say that the first digit you see is 4. Well, knowing that 4 was selected for that first digit has no impact on the probability of anything else being selected subsequently. Okay, so it doesn't change the probability. It doesn't impact any other outcomes. Okay. All right, so not only does each entry in the table, okay, not only is each entry equally likely, but each subset of size n is also equally likely. Okay, so it is truly random. So here's how to use a SRS. Here's how to use the table to choose an SRS. And it's table D. I don't know why I kept saying table B. It's table D, is the table of random digits. Okay. So the first thing is you're going to label. You're going to give each member of the population a numerical label of the same length. That's important because otherwise the table won't work, okay, of the same length. So let's go back to my hypothetical example. Let's say that my population of interest is all high school seniors in the Tri-Valley area. And let's suppose that I happen to know that there are 5,000 high school seniors in my entire population. So that is capital N. Capital N stands for population size. So capital N equals 5,000. And from those 5,000, I want to draw a simple random sample of size n equals 500. Little n equals 500. Okay, how do I do that? Well, step one is I have to number every student. And so what I'm going to do is I'm going to get a roster of all 5,000 of those names. And the order that the names appear on that roster does not matter. I can put them in alphabetical order. It's not going to mess up my randomness. Okay. So let's just say I get an alphabetical roster of all 5,000 currently enrolled high school seniors in the Tri-Valley area for the entire population. Then what I'm going to do is I'm going to number them. Okay. But the numbers have to have the same length. So starting with that first name, I'm going to number that first name 0000. Yeah, I'm going to use 4 digits because obviously I have 5,000 total students, so that any of the students after 999, they're going to have 4 digits, right? And so all of my labels have to be of the same length. So I'm going to start with 000. You could actually start with 0000, but typically the convention is to start with 1. So instead of 0000, I'm going to start with the first name on my list. I'm going to label that 0001. Then the next one is 0002, 0003, all the way up to the number 5,000. Okay. All right. So I label everyone. Okay. Step 2. Step 2. I read consecutive groups of digits of the appropriate length. So my length is 4. So I go to table D and I start reading the numbers from left to right 4 digits at a time. Okay. And so when I look at those first 4 digits, let's say my first 4 digits, my first group of 4 digits that I read on table D, let's say it's the numbers 2357. Okay. Well, that corresponds to student number 2357 on my roster. Okay. And so I circle those 4 digits, 2357, and then I find that student, okay, that student's name. Okay, and then that student is my first student in my sample. Well, let's say I get to a group of 4 numbers and it's beyond 5,000. Let's say my group of 4 numbers is like 6523. Okay, well, I don't have 6,000 people in my population. I only have 5,000 people in my population. So what do I do with 6523? I just put an X through it. I just line through it, and then I go to the next 4 digits. Okay, I line out that entire 4 digits that's not in my population. Okay, and then when do I stop? I stop when I have selected 500 students. And that is how you use table D to create an SRS. Okay, so here's an example from the textbook where we have all these different types of hotels, and I believe that these are hotels in Hawaii or something like that. And so out of all of these hotels, use table D at line 130 to choose an SRS of 4 hotels. Okay, so at line 30, that means start on line 130, and we read from left to right. Okay, we start at the leftmost entry and we read from left to right. Okay, so these are the names of all these hotels, and we want to randomly select an SRS of 4 of these hotels. Okay, so here is the line. Here's line 130 from table D. Okay, and so we just read these 2 digits at a time because all of these labels have 2 digits. It goes from 01 to 28. Okay, so my first 2 digits, okay, are 69. Well, 69, that's too high because it only goes to 28. So I just put an X through that. Okay, 05, well, that works. So I would circle that on the test. On the test, on the paper, the paper test, they'll give you like an actual, this will be written down. And so instead of like stars and red box, you're just going to circle it right on the excerpt. Okay, so put a line through that or an X through 69, circle 05. Then my next 2 digits is 16. And even though there's a gap here, there actually is no gap. They just create these gaps to make it easier to read. Okay, so 16, yes, that works. That is number 16. That's the Radisson. Okay, and 5 was Beach Castle. Okay, that works. 48, well, that's too high. So I put a line through that or an X through that. And then 17, well, that works. That's the Ramada. Okay, then my next two digits are 8, 7. Nope, that doesn't work. X, 17. Well, I got 17 already, and in this case, I'm going to skip repeats. Okay, and that's important to put that in your instructions, skip repeats. Okay, and then where am I? I'm at 4, 0. Well, that's too high, so I'm going to cross that out. And then 9, 5, well, that's too high. Well, 17, that's a repeat again. 84 is too high. 53 is too high. 4, 0 is too high. 64 is too high. And we go on and on and on and on and on until we actually get to 20. Okay, 20. 20 is going to work. Okay, and so that's the C club. And now I have 1, 2, 3, 4, and I'm done. Okay, so those are the 4 hotels that I've chosen as my SRS. Okay. So our SRS of 4 hotels is the Beach Castle, the Radisson, the Ramada, and the Sea Club. Okay. Now again, it doesn't matter what order you put these in. And it looks like here we just put them in alphabetical order and we just number them from 01 to 28. That does not matter. What does matter is that the number labels have the same number of digits. Okay, and that you tell the reader which line of table D you're starting from, and that you also tell the reader that you're reading from left to right, and that you're skipping repeats. Those are very important to include in your instructions. All right, so once we have an SRS, we're going to gather data from the SRS, and then we're going to make an inference or a conclusion about the entire population. Okay, but sometimes in our SRS, we have homogeneous subgroups, okay, things that are called strata. Okay, sometimes within, not in our SRS, excuse me, sometimes within our population, we have some homogeneous subgroups. And we want to make sure when we're sampling, we want to sample in such a manner that those homogeneous subgroups are represented in our sample. Okay, because if we just do a straight up SRS, it is possible that we would miss some of those homogeneous subgroups and that our SRS would not really represent our population that well. Okay, so for example, in our hypothetical example of the population is those 5,000 high school seniors that are currently enrolled in high school in the Tri-Valley area. Our question, depending on what our question of interest is, we want to look at, are there homogeneous subgroups where the characteristics, we want to make sure we have them included, all the different homogeneous subgroups included and represented in our SRS. Well, it just depends. It depends on what the question of interest is. Okay, so let's say that my question of interest is, well, what is the average, what is the height? What is the height of high school seniors in the Tri-Valley area? And why would we want to know the height? I have no idea. Maybe we want to compare the height of high school seniors in the Tri-Valley area to the height of high school seniors on the East Coast. I don't know. I have no idea. But let's say that is our question of interest, is how tall are high school seniors in the Tri-Valley area? Okay. Well, if that is our question of interest, then what we might want to do is we might want to look at some homogeneous subgroups within our population, and we might want to stratify our sample. Okay, and we might want to look at okay, maybe we want to look at the strata of gender, and maybe we want to make sure that we include males and female, because the thing is, if we do an SRS, is it possible that our SRS of size n equals 500, is it possible that we would get all 500 of them are male? It's possible. Okay. Is it possible that we would get all 500 are female? That is possible as well. Maybe it's not super likely, but is it possible that one of those genders would be overrepresented and one would be underrepresented. Yeah, that is possible. So one way to address this is to make sure that we have a representative sample and we're going to call this a stratified random sample. And by the way, with gender, what about other categories other than just looking at gender from a binary standpoint? What about people who identify their gender in a different way other than just male or female? Is it important? Would it be important to include different strata? And it may very well be. It may be extremely important to represent, the different strata, the different homogeneous subgroups within the population. Okay, so you might have one strata that's male, one strata that's female, another strata that is maybe trans. Maybe there's a strata of non-binary. And so, yeah, there may be several different strata that you would include in this sampling technique. And then what you do is, once you divide up the population into the different homogeneous subgroups or the different strata, then you just do SRSs from each one of those strata. Okay? And that's how you make sure that your sampling technique is inclusive of all the important strata that would impact your output variable or your output or your whatever data it is that you're gathering. Okay, so to select a stratified random sample, just classify the population into groups of similar individuals called strata, and then just do SRSs from each one of the strata. Okay, so here's an example of out of the textbook. So sampling sunflowers. Okay, so use table D or technology. So they're saying you can use math, PRB, randint. Okay, but use table D or technology. Let's go ahead and use table D because it's the longer way and there's kind of like more practice to be done there. So let's use table D to take an SRS of 10 grid squares using the rows as strata. Then repeat using the columns as strata. Okay, so how would we do this? So we have, here are your columns, A, B, C, D, E, F, G, H, I, J, and here are your rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this grid system is basically a farm of sunflowers. Okay, and so there's all these sunflowers, and we want to make sure that we select sunflowers from all the different geographic locations on the sunflower farm. And so we think of this as a stratified random sample. Okay, so we think of first, we're going to take the rows as the different strata. So what we mean is, like, if we have all of these sunflowers and we want to sample, okay, take an SRS of 10 grid squares. If we want to take a sample, if we just do an SRS of this entire sunflower farm, we might get all sunflowers like from one particular area of the farm, and we don't want that. And why is that? Because the sun exposure might be different. The soil acidity might be different, in this one particular area. We want to make sure that we kind of spread out, okay, and make sure we get some sunflowers from, lots of different, from each one of the different rows, okay, and then we're going to do the same thing for the columns. Okay, so how do we do that? So with row 1, we have A, B, C, D, E, F, G, H, I, J. Okay, so we're going to call this, we can call this 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, 10. Okay, that won't work. Sorry, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. Okay, so these are all labeled by 2 digits. Okay, so then we just go to table D and we pick a particular row number. It doesn't matter, like picking which row of table D does not matter. Okay, so we're going to go ahead and grab your book. Okay, I'm looking at table B. And okay, sorry. So in our textbook, it is table B as in boy. That's why I kept saying table B. In other textbooks, it's table D. Okay. In our textbook, it's table B. It's at the end of the book. And let's just choose like something right sort of in the middle of the arbitrarily, let's just choose, not randomly, but arbitrarily, let's choose line 126. Okay. So when I look at line 126, okay, I'm looking for a 2-digit number. So I have 96, that doesn't work. 92, that doesn't work. 71, that doesn't work. 99 doesn't work. 31 doesn't work. 36, 80, 97, 41, 92, 77, 56, 78, 87, 41, 48, 40, 94, 19. Finally, okay, 19. So I'm going to pick this grid right here, which I've labeled 1, 9. Okay, now I'm going to do the same thing for row 2. So we're going to call this 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 9. Okay, and for this, I can start on a completely different line, or I can just keep going. It does not matter. Okay, so if I just keep going, okay, I go to 0, 3, then I just wrap around to line 127. So 4, 3, 9, 0, 9, 9, 9, 4, 7, 7, 2, 5. That's my next selection, 2, 5. So it's 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. So that's this grid square right here. So I could put an X there, I could put an X there. Then I can just keep going, and I can keep going until I've selected one grid square from each one of these rows. And then I can do the same thing for the columns. Okay, so that is how that works. Other sampling methods. Okay, so one other sampling method, there's actually 2 other sampling methods that are legitimate that I'm going to talk about. Okay, but the next one that's widely, universally accepted is called the cluster sample. Okay, it's called the cluster sample. So the idea of a cluster sample is I want you to think about a cluster sample as opposite of a stratified random sample. So it isn't truly opposite at all, but it will help you to remember the definition of and the distinction between what is a stratified versus what is a cluster sample. Okay, so let's just think about a stratified sample. I told you that with a stratified sample, it is you have homogeneous subgroups, right? You have homogeneous subgroups, and so you have all these homogeneous subgroups within the population, right? And you want to make sure you take an SRS of each one of those homogeneous subgroups, okay? With a cluster sample, it's different. With a cluster sample, you have heterogeneous subgroups, okay? And what I mean by that is you have clusters within or groupings within your population where each cluster it has all the heterogeneity, it has all the variation, all the variety of things that you're really looking for in your sample. Okay, so you would think of each cluster as being a representative sample. Okay, so each cluster is kind of like a microcosm of the entire population. Okay, and so in that case, you can simply select one of those clusters. Okay, and from that cluster, what you can do is just SRS, okay, within that cluster. So here we go right here. To take a cluster sample, first divide the population into those smaller clusters or those smaller groups. Ideally, these clusters should mirror the characteristics of the population. So each cluster is a microcosm of the population. Each cluster has all the heterogeneity, all the variation, all the variety of the entire population. So then we're going to choose an SRS of the clusters. All individuals in the chosen cluster are included in the sample. Okay. So if you want to know something about all high school seniors in the Tri-Valley area, okay, you might think about each one of the high schools in the Tri-Valley area as a cluster. Okay, and that is if you are okay with thinking that like each high school, yeah, it has enough variation within that high school to be representative of the variation of the entire Tri-Valley area. Okay. So would you include a school like, I don't know, like De La Salle, as one of the clusters that represents all high school seniors in the Tri-Valley area? Probably not, because De La Salle is a very expensive private school. It's a Catholic school. They have, it has its own culture. It has its own sort of, um, set of values and things, priorities. And is it represent? It's probably not representative. But what about a large public high school, like Dublin High? Could you say that Dublin High is kind of a cluster? Does it have all the kind of variation that you would be looking for in terms of representing the entire population? Yeah, it very well may. Okay, you might think that Dublin High and any of the large public high schools in the Tri-Valley area, you might think of them as clusters. Okay, and so then you choose an SRS of the clusters. So you randomly select which cluster you're going to use, which ones of the clusters you're going to use, and then you use all the high school seniors. And let's say that you randomly select between the high schools. And how would you randomly select between high schools? Well, the same thing. You just number them. Okay, so maybe Amador Valley High School would be number 1, Foothill would be number 2, Dublin High would be number 3, Monte Vista number 4, San Ramon Valley number 5, Cal High number 6. I forgot Doherty Valley number 7. Then you would just use the table of random digits or use your calculator, Math PRB randint 1, 7, and you would select. Okay, and that's the high school you would go with. All right, so here we have a school assembly. So the stage is this blue thing up here. So that's the stage. And then here's where the audience is sitting. Okay, and so describe how you would use the following sampling methods to select 80 students to complete a survey. So here are the students where they're seating, but notice they're seated by grade level. There's 9th, 10th, 11th, and 12th grades, right? So the 9th graders are seated in 601 to 800. Okay, 601 to 800. So I see 800, and they're from 601 to 800. Okay, okay. The 10th graders are from 401, seats 401 to 600. The 11th graders, 201 to 400. And the 12th graders, of course, the 12th graders get the best seats in the house. They get to sit in the very, very front rows. Okay, and obviously this doesn't show all 800 seats, but it gives you an idea that seat 1, is in the very front, and then it just follows this numerical order. Okay, 1 through 20, then 21 through 40, then et cetera, all the way to 800. Okay, so how would you select a random sample of size n equals 80 students? Okay, how would you do an SRS from this? Well, using table B or your calculator, okay, Math PRB randint, okay, what would you do? Well, the seats are already numbered, but the only issue is that they're not the same number of digits, right? So instead of this seat just being number 1, you would have to make this 001, 002, 003, etc. You want to use 3 digits because obviously the largest number has 3 digits. Okay, and then this is how you would write the description of how you selected an SRS using table B. Okay, you'd say first, and this is what you would be writing in your AP exam, because in your AP exam, they're going to ask you this type of question. Describe how you would, in this situation, draw an SRS of size n equals 80, okay, using table D or table B or whatever they call it, the table of random digits. So you have to write out instructions. So step 1, number each student or number each chair with the same number of digits so that this is 001, 002, all the way to 800. Okay, that's step one. Step two, starting on line number, and you just write in whatever line number you want to start on. Starting on line number, I don't know, let me just pick a line number. Line number 106, starting on line number 106, reading from left to right, read 3 digits at a time until you have selected 80 unique 3-digit numbers that are between 001 and 800. And step 4, skip repeats. You always have to say skip repeats. The reason why saying skip repeats is so important is because in some processes, you do not skip repeats. And in some processes, you do have to skip repeats. In SRSs, when we're using table B, we are going to skip repeats. So we have to say that we're skipping repeats. Okay. And then finally, when you're describing your answer to this, okay, RSRS was, consisted of, and then you'll just write down all the different numbers. Like on line 106, the first thing I see is 684, so that works. Then 173, so that works. Then 501, then 315. So you'd list out all those numbers. Okay, now the calculator shortcut to this is Math PRB. So if you turn on your calculator, Math PRB, randint, and then the parameters you're going to put in, or I should say the arguments you're going to put in are 001, comma, 800, and in your calculator you don't actually have to put in 001. In your calculator, the labels don't have to be the same number of digits. You can just put in 1, comma, 800, comma, 80. Okay, and 80 is the sample size. Okay, press enter, and then it's going to give you 80 unique numbers between 1 and 800. Okay, inclusive. Okay, so now the more important thing, how would you do a stratified random sample and how would you do a cluster sample? With a stratified random sample, the strata are probably the different grade levels, right? 9th graders, 10th graders, 11th graders, and 12th graders. So let's do an SRS of size n equals 20 for your 9th graders, same thing for your 10th graders, same thing for your 11th graders, and same thing for your 12th graders. So you just describe how you did that, okay? And that way you would have 20 9th graders, 20 10th graders, 20 11th graders, and 20 12th graders. What about a cluster sample? Well, for a cluster sample, how can I get a cluster that is representative of all 4 grade levels? Well, it's not going to work by row, obviously, because students are seated in grade level by row. So instead of by row, you would go by columns. Okay, you would go by columns like this. Okay, so this column, okay, would be one column, then this would be a column, this would be a column, this would be a column, et cetera, et cetera. So there's 20 of these columns. Okay, so you'd randomly select, how many of those columns you need, and then those would be the columns that you would use. Okay. All right, inference from sampling. Okay, inference is why we do sampling, because we want to infer something about the entire population. Okay, so the purpose of sampling is to give us information about the bigger population. The process of drawing conclusions about a population on the basis of sample data is called inference. Inference, by the way, is half of AP Stats. Like, that is the big topic. That's Roman numeral number 4. That's the big topic that all this other stuff we're learning is to get us to inference. Okay. So why do we rely on random sampling? First of all, it eliminates bias in selecting samples. Okay, and number 2, the laws of probability allow trustworthy inference about the population. So results from some random samples come with some margin of error that sets boundaries on the size of the likely error. Okay? And then larger random samples give better information about the population in general than smaller samples. Okay. So what are some things that can go wrong? Well, there's always going to be some kind of error. So good sampling technique, utilizing good sampling technique reduces the error. Okay, reduces the sources of error. All right, so here's some things that can go wrong. Okay, here are some errors that, so there's errors, and then there's also, yeah, anyways, sorry. Let's go to some of the errors some of the things that can come up. So one is undercoverage. And undercoverage is when some groups in the population are completely left out of the process of choosing the sample. Okay, undercoverage. Some groups in the population are left out when you're designing your sample. Okay, non-response. Non-response occurs when people do not respond. And why do they not respond? Either they choose not to respond or it's impossible to contact them. You cannot contact them. Okay, so either they just refuse to fill out your survey or you're not able to contact them. Okay, that happens a lot with phone surveys. How many times have you guys, been called on your cell phone and someone's asking you, "Hey, will you take 2 minutes to, answer a few questions?" Click, no thanks. And then there is what's called response bias. A systematic pattern of incorrect responses in a sample survey leads to response bias. And that is this funny little cartoon, this Calvin and Hobbes. And it's pretty funny, right? So I'm filling out a reader survey for Chewing magazine. See, they asked how much money I spent on gum each week. So I wrote $500. For my age, I put 43. And when they asked what my favorite flavor is, I wrote garlic curry. This magazine should have some amusing ads soon. I love messing with data. And that's exactly how all of us have felt at some point. We all have that little kind of, cynical side to us that's like, oh, let's just skew all the data by, putting in some ridiculous answers. We've all thought that, or maybe even done it at some point. What's interesting now with artificial intelligence and machine learning and social media, and with social media selling out to big time advertisers and marketing companies, is that what you do on your cell phone really does. And this was before Calvin and Hobbes. This was back in the 1980s. This was before cell phones were even invented, or certainly before smartphones were invented. But this is salient today, right? This magazine should have some amusing ads soon, right? That's the same as your social media. If you put in a bunch of interesting, weird stuff into your phone, especially on social media programs, apps, you'll get some really interesting advertisements. Okay, and then finally, question wording can also systematically influence respondents to respond in a particular direction or in a particular manner. So wording of questions can also be a type of bias, okay? All right, so that's what we've learned. And what we will learn coming up is experimental design. Okay, and there's quite a bit. Experimental design is pretty heavy. So thanks, guys. Have a great day, and we'll see you in the next lecture.